to lecture 4. So if you haven't noticed yet, we uploaded homework 2. It's on Canvas. Please look at it soon, please. It's like 3 times harder than homework 1, probably. It's very hard. So definitely look at it as soon as you can. Like I said in the Piazza post, try to come to office hours as often as you can. Make sure you have groups. They're very valuable. So yeah. I was afraid of that. We'll see how that works. Okay, so homework 2, then we're going to have an exam. It was supposed to be next week, but because July 4th there's no class, I'm thinking we don't do it next week. So it'll probably the following Monday instead. Just an update to the schedule. And then next Wednesday we'll do graph algorithms instead of greedy algorithms. That's kind of the tentative plan. So the exam will be next Monday. And then graph algorithms next Wednesday. Okay. Other things, we're probably not going to do the problem-solving journal again. That's probably just for homework 1. I'm sure no one's disappointed. Yes.
It's still 30% of our final grade.
No. No. So what we'll probably do is for homework 1, we'll just combine the 2 scores proportionally. And then going forward, it's just going to be 50% for homework. Any other questions? Okay. So today we're going to talk about dynamic programming. But first, I just wanted to review recursion and reductions a little bit and just keep punching into your mind the key themes we've seen up so far. So what are some of those themes? Well, one of them is to have trust. So whenever you're doing a reduction or recursion, you need to trust the thing you're reducing to. So for the case of recursion specifically, this means trust the recursion fairy, don't unroll. And in general, all the time you're reducing the things, even if you don't realize it. So every time in any programming language you do an addition operation, do you really need to think about checking the ALU to see if it's doing it properly? Probably not. You kind of just trust it. And so you just want to keep trusting more complex algorithms too. So whenever you feel the urge to unroll the recursion, just remember, do you feel the need to check the ALU every time you do addition? And then apply the same logic. Okay. The other thing that's really important is start small. So this basically means, you're trying to solve a problem. Don't go for some complicated algorithm first. Start with something really easy, and then make it faster after you have something that works. So make it correct, even if it's a dumb algorithm, then make it fast. Okay? So those are some of the key themes. The other one that's kind of built into trust is, recursion is induction, and induction is our friend. This is extremely important, so if you're uncomfy with induction, you got to accept it. It is your friend. It will help you with proofs all the time. It's a critical tool we use all the time in algorithm design. So just want to reiterate those points. And I thought it'd be also useful to go through an example of binary search. So I'm sure everyone has seen binary search before. It's probably the first thing you saw in computer science, like CS200. But let's go through this now using our formal recursion framework. So the problem, as you know, you have a sorted array A right here. And your goal is to find a specific element X. You want to find the index. So for this instance, you're looking for the solution 3, because that's where 6 is. Or you report that the thing you're looking for is not in the array. And how do you do this? What's the algorithm to do this? Well, you're going to look at the middle element. M. If M is equal to, or if the array element at M is equal to X, then we return M. Otherwise, we're going to recursively search one half of the array. Otherwise, search the first half. It's just M minus 1. Or the second half, depending on AM being less than X or AM being greater than X. Okay? So that's our algorithm. So visually what we're doing is we just stab this array in the middle. So let's say the one we look at first is this index. We compare 15 to 6. 6 is smaller than 15, so because the array is sorted, we know it has to be in the left side. So X has to be in the left side because the array is sorted. Okay? Now how do we find 6 in the left side? This was a mistake. Luckily, I have a solution. I didn't want to wear my necklace again because it kind of made static, but I guess it was useful. Now it'll never fall off. Okay. So how do we find 6 in the left side of the array? What's the answer? I heard someone say fairy. Yes. We don't. The recursion fairy finds it in the left side. It is none of our business. We don't care how she does it. We have to trust her to do that task for us. Okay? So that's the algorithm. Pretty simple. Of course, the base case kind of built into here. What's the assumption we're making? Well, we're assuming there's a middle element, right? Which means there's some elements. So if A is empty, i.e. there's no elements, then we return none to indicate, it's not in the array. There's nothing in the empty array. Okay? So now let's think about the correctness, right? So how do we prove this correct? Induction, of course. Now remember, we want to induct on some measure of progress. So what's our measure of progress in this algorithm? Well, it's the number of elements left that we have to check, which is equivalent to the size of this smaller array. So at each point, we reduce the problem to a smaller array that constrains our search space, and that's going to be our measure of progress. So we're inducting on the size of the array. Okay, so what's the base case? Well, that's when A is empty. In other words, the size of A is 0, and the algorithm is correct in that case because it returns none. And as I said before, obviously, you can never find any element in an empty array. Okay, so what's the inductive step? So the size of A is greater than 0. There exists some elements, so there exists a midpoint. So we know there exists a midpoint. And so we can do that procedure. Clearly, if AM equals X, we're done. And we correctly return M, which is the right answer. Otherwise, either the element is in the array, or let me say either X is not in the array, or we know X is in the left side. Let's just focus on the case where AM is less than X. So for this case, we know it's in the left side. Why? Because A is sorted. And now what's the last step? We do nothing. We let the recursion fairy solve it. And then the solution, the final solution, is correct by the induction hypothesis, because the induction hypothesis just says the recursion fairy's part is correct. Okay? So binary search, it's really intuitive. You've all seen it before. But when we think about it through the mathematical algorithmic lens, this is kind of the structure we want to approach it and think about it. So you don't have to worry about what's on the left and right side. You just have to trust that the recursion fairy can correctly find those things. What's the runtime analysis? You know it's O of log n, but why? Well, we can write the recurrence, T of n is equal to T of n over 2 plus O of 1. Why is this? Well, because we reduce to a subproblem that's half the size of the original array. We look at 1/2 of original array. And then this is just to do the, comparisons with AM. Okay? Now, what's the solution to this recurrence? Well, it's going to be O of log n. Why is that? Well, you can make a recursion tree. It's just going to be a single path. So if we did that, you get this little tree that just looks like this. Each time you just get a 1. And the total height of the tree is log n, because that's how many times we divide n by 2 before it hits 1. So that's why it's O of log n. You could prove it by induction. You could just see it's dividing by 2 and be like, it's just like merge sort. However you want to think about it, that's why it's O of log n. Okay? So this is basically the overall thing you're going to do every time you have an algorithms problem. You're going to state the problem, or whatever problem you're going to solve, understand the problem, what's really asking. You're going to write your algorithm in pseudocode, or whatever pseudocode-like thing you want to do. Your proof, your correctness argument, which for recursion is going to be induction. Usually it relies on the recursion fairy. And then your analysis is recursion trees. So any questions on this? This is just one full example of the entire process when you're doing a recursion problem. Hopefully this is all reviewed, just I wanted you to see the full process. Any questions? Okay. So now let's talk about Fibonacci numbers. So if you're very mathematically inclined, you've probably heard of Fibonacci numbers. They're supposed to quantify breeding patterns of rabbits. So these are supposed to represent breeding patterns. This isn't important for the course, I just think it's hilarious. Of rabbits. I just really want to know, were there that many rabbits around to where they needed to create a formula for this? I don't know. We may never know. But Fibonacci knows, and that's what matters. So this is the definition of the Fibonacci number sequence. So if we write it out, it looks like 0, 1, 1, 2, 3, 5. And this is basically a recursive algorithm. So you're just going to look at the previous two, add them up, and that gives you the next one. So we add these up, you get the next one, and so on. So that's what the sequence is. Now our goal in this problem is just to compute these numbers. So obviously we can do this by recursion. I would almost argue this is already an algorithm, just saying it like this. But let's write it out in its entirety. So first, what's the problem we want to solve? We're going to solve fib of n. This is going to return the nth Fibonacci number. Okay. And the algorithm, you can almost read it right off of the formula. If n equals 0, return 0. If n equals 1, return 1. Otherwise, return fib of n minus 1 plus fib of n minus 2. And that's basically the entire pseudocode. Okay? Now, correctness, we literally took the formula and plugged it into an algorithm, so I think that's obvious. But what about the running time? So how fast does this look? Does this look like a slow algorithm, or does it look pretty fast? Why do you think it's slow? Who thinks it's fast? Let me start with that. No one thinks it's fast? It's just two if statements and then you're summing things. Why would it be slow? Did everyone just read ahead? So the answer is it is slow, but really why should it be slow, right? All we're doing are if statements and a sum. It seems like it should be pretty easy to compute that. So we only have if statements and pluses, so it should be easy. So what's going wrong? Because in fact, this is exponential time. So the running time is going to be theta of phi to the n, where phi is the golden ratio, which is like 1.6. So this is actually exponential time. It's not n cubed, not n to the fifth, exponential, which is like the worst thing we could hope for. So if we just looked at the recursion tree, pretty big tree here. So what's happening? Well, if we compute f of 7, we compute that once, and f of 7 requires, say, f of 4. So eventually to compute f of 7, we first have to compute f of 4. And notice we compute f of 4 a bunch of times. And if we looked at, say, like f of 1, we compute this a ton of times. In fact, we have to compute f of 1 f of n times, because we're just summing up a bunch of 1s at the bottom of the tree. So the issue here is we're kind of repeating work that we've already done unnecessarily. That's the issue. So we are repeating work. Is there any good reason we should repeat all this work? No, there's not. So what's like the easiest way you could deal with this problem? What do you all think? If we're repeating work a bunch of times, is there a way we could just avoid that? Yes?
Store the result of certain operations.
Yeah, so we could just save the answers like to an array. And then every time we need them, we just check the array instead of recomputing it all from scratch. So let's try that. Let's just save partial solutions somewhere. So if we do that, then we'll have like, say, array f. F is an array from 1 to n. We'll start with the array just being all zeros. And then what we're going to do is modify this step of the algorithm. And what we're going to do is just do a check. So if we've already computed f of I, or let's say n, then don't recurse. Otherwise, we're going to define the solution to be f of n. So before we return the answer, we're going to save it to that array entry. Okay? So that's the new algorithm. Let's see how fast that is. So that technique is called memoization. There's no R there for historical reasons. I honestly don't think you should care about that. Just call it memorization because that makes more sense. But if we do that, this is just the idea of using an array or using some kind of storage to avoid recomputation. So if we do this, this is the new tree. All these things in gray, we aren't doing anymore. None of these are going to be computed. That's our savings. So that's more than half the tree. So that's a huge improvement in runtime. And if we look at the recursive calls now, notice we're only going to compute these things exactly once. So f of 5 appears once, f of 4 appears once. Each of these, other than the base cases, appears once. Or twice, to be precise. Okay? So we went from this exponential tree to a tree that has 2 things per node. So it's roughly 2n sized instead of theta of n. Okay? So we went from an exponential sized tree to a linear sized tree, which is a gigantic improvement. We didn't go to n squared, we didn't go to n cubed. We went all the way to pretty much the best thing you could possibly do. So any questions about this so far? We had a simple recursive algorithm that was slow because it was repeating itself many times. And so we just added the ability to store things, partial solutions, and then now we get a much faster algorithm. Clear to everyone? Any questions? Yes?
When do you start taking into account the space it takes to remember every single pass result?
So when does it become important? In this class, it's never important. So generally, there's a trade-off between how much space you use and how much time you use. So there's a trade-off between time and space. Usually space is the most important resource, but it's, like in practice, as long as you're not using too much space, like you're not using O of n to the 25, you're probably okay. Polynomial is usually your benchmark for goodness. But yeah, that's a good point. So in the original, how much space are we using? Just constant. You're just saving like a single number each time. Now we have to store n numbers. So our space increased from constant to linear. but our time decreased from exponential to linear. So whenever these two things are equal, that's a pretty good algorithm.
But then do we need to have everything stored? Do we not?
No, we don't. So that leads perfectly into the next part, which is up there, what we did was recursion with memorization. So we didn't use a recursive algorithm, and we just stored things. And by accident, we kind of got a solution that was fast. And it does this in some order that we can't really predict. It just depends on how the stack's going to function that day. So instead of letting the recursive algorithm kind of fill up the array in some order accidentally, let's just directly fill up the array. So instead of recursion filling array in some order, or in other words, instead of them computing the partial solutions in some order, we're going to just do it directly. So we just look at what the algorithm's doing. Notice there's these dependencies here. In order to compute f of 5, you first have to compute f of 4 and f of 3. So if we look at how this array is being filled, it's got to be filled from smallest element to largest element. There's no way you could have computed f of 5 before computing f of 3, because it depends on one another. So if we looked at the filling process, it's going to fill up the array from f of 1 all the way up to f of n, in that order. So we can just deliberately do that. So here's the pseudocode. We first fill in the table, fill in the base cases. So these are the smallest fib numbers. And then we're going to keep filling up the table, growing the tree from the bottom up. So that's something you're going to hear a lot, is bottom up. So this is different from top down, which is usually how you do recursion on trees. So normally you start at the root, you look at the left and the right side, and then you keep doing things down and down the tree. But here we're doing the opposite. We start at the leaves, which are the base cases, and we build the solutions up to the root. Okay? So this will always guarantee we compute f of I before f of I plus 1, because we deliberately fill the array in that order. So the space here, it's still O of n, but now we can tweak this. We can make this a previous, and we can make this a current. And then we just need to look at previous press current, and then update current. And we update all those parameters. So overall, if we look at the full pseudocode, it's going to look like this. So here our space is constant. Constant space and O of n time. And you don't even need recursion trees to analyze this algorithm, because it's just a for loop. But remember, for loops are also recursion. Okay?
You could call for loops as recursion.
For loops are recursion, yeah. You can think of it as like a tail recursion. Anytime you're iterating a process, you're doing the same thing every time. But now it's a smaller problem being a larger I. So smaller n minus I.
I thought maybe just function calls are more like recursion.
Function calls generally aren't recursion, but it depends on what the function's doing. But if you black box it, if I just gave you a function f, and I didn't tell you anything of what's going on inside f, then that's not recursion, it's just a reduction if you use f. So here's another example of where you want to start basic and then improve it. So you could have just started out and said, hey, we really only need 2 parameters, but we didn't do that. We did it in steps. We started with the intermediate version where we saved everything, and then we noticed that we could improve it by having only 2 parameters. But it's important that we started here and then got faster, because if we did the opposite, this algorithm is iconic for having off by 1 errors. So even if you think it's correct, it might have had a bug. So it's always better to just start with the simpler algorithm first, and then try to make it fast. Okay? So any questions on that? Now, if you're ever asked to predict breeding patterns for rabbits, you'll be able to do it very efficiently. Yes?
For like the Fibonacci numbers, like used for like anything else when predicting breeding patterns.
Yeah, they're used in Fibonacci heaps, which is like the fastest data structure of all time. And then, other than that, I think they're mostly used in like science rather than computer science, like studying physics and stuff. But in computer science, they're useful for Fibonacci heaps. But this general pattern of computing a sequence of numbers, like it doesn't have to be fn, but just some sequence, that comes up a lot. Okay? So one last thing. I just want to, just a spoiler. So this is O of n only if adding 2 numbers is constant. In other words, we're doing O of n additions. But the total runtime is not actually O of n. It's O of n squared, because adding to n-bit numbers takes O of n time. So if we're doing O of n additions and each addition's O of n time, then it's O of n squared total. This isn't super important for this specific algorithm because, you can always take addition for granted. But for more complicated problems where your precision of arithmetic's important, like for subset sum, this will be an important point. Okay? So let's return to our example of text segmentation that we did last time. So remember, you have some kind of giant list or giant array of letters. And your goal is to split up that list so that you're basically adding spaces. Each of these should be a word. So between each space you add, that should be a valid word. And then recall we came up with the splittable function to compute this. So what's splittable of I? This is exactly the subproblem in the middle of the process. So we're assuming we've already solved the problem for a1 up to I minus 1. And now we have to decide where the next word goes. So we want to add the space breaks for this subarray ai through n. So how do we do this? Well, if I is greater than n, the array is empty. And so obviously you can split up an empty array by doing nothing, and that's a valid word vacuously. Otherwise, if A is not empty, you have at least one character, and then you're going to basically look at every possible word that starts with AI. So you're going to try every possible AI through J, check if it's a word, and then recursively add line or space breaks for the rest of the array. So that was our recursive backtracking strategy to solve the splittable problem. And we didn't really talk about it much, but this is a very slow algorithm because you potentially have to check all of these subsequences of the array. Okay? So the question now is, we already have this recursive algorithm. Can we add a similar memorization structure to the algorithm to make it fast? So, how to add memorization to make it fast. So one thing to notice is that isWord I of j, that can only be called on at most O of n squared possible indices. So there's only O of n squared inputs to isWord. Why is that? Because you have n choices of I, n choices of j. So we know we'll only ever call isWord O of n squared times. So we'd expect the algorithm truly to be O of n squared, not O of 2 to the n. So what's the obvious thing that we could try to memorize here? Using the Fibonacci as an example. Yes?
I'm not sure if I'm getting why it's squared.
Well, we think it'll be O of n squared. Just because, think of the possible inputs to isWord, the possible ij pairs. How many total pairs could you plug into isWord? Unique pairs, I should say. Like obviously you can use the same I and j many times, but if you just want the number of unique pairs I and j, there's n choose 2, which is O of n squared. Or you could think of it as there's n choices of I, n choices of j, and so n times n. So what thing here are we possibly repeating many times? Well, let's draw out the recursion tree. So we're computing split of n. I'll just call it S of n. So let me make it a little bigger. So when we compute split of n, we have recursive calls to split of n. Actually, this will be split of 1. So we call split of 2. That's just the case where we plug in j equals 1. Then j plus 1 will be 2. We also have a call for S of 3. That's just the case when j is 2. Then this will be 3. And so on. We do this for every possible n. So we're going to get branches all the way up to S of n plus 1. Now let's repeat this idea. When we call split of 2, we're going to recursively call split of 3, split of 4, all the way up to Sn plus 1. So on, we have S of 4. So we already can see where this is going. We're calling the splittable function a bunch of times. So you see here S of 3 already is appearing twice. So what thing do we want to try to store into memory? Yes.
The result of splittable.
Yep. So we're always going to, essentially we're replacing splittable with an array S of j plus 1. So we just save the partial solutions to an array, then we can just call the array instead of recomputing that value every time. Yes?
You lost me with the recursion. Are each of the children like that we do the one-letter thing, then the two-letter thing, then the three-letter thing, or no?
So this is, each of them do that for all n.
Okay.
So for each child, they branch that many children themselves.
So is S2 a child of length 2, or am I missing?
S2 is when you plug in I equals 2.
Okay.
So S1 means you plugged in I equals 1. And if you plug in I equals 1, you basically have a for loop here that's going to call a recursive call for each j from I up to n, well, specifically j plus 1. So if you're in splittable of 1, you're going to call splittable of 2, splittable of 3, splittable of 4. You're going to call all of them, basically, just from the top. So in the picture here, from the very first call, you're going to get n recursive calls. Then from each of those children, you get something close to n as well. So for S of t, you get n minus 1 recursive calls. For S3, you get n minus 2, etc. So the tree is growing exponentially. Yes?
The result to n plus 1 is
So n plus 1 is our base case. That's when we fall off the array. So here, you know, j can be n, and then you call n plus 1. Other questions? So as you can see, just from looking at the recursion tree, you're repeating a ton of work unnecessarily. You keep computing S of 3 and S of 5 tons of times when you really don't have to. So the idea is we're just going to store each of the splittable calls into an array. And specifically, S of I will hold the result for splittable of I. So at the very end, you would be returning S of 1. That's your final algorithm result. Okay? Any questions on this? So that's the idea. We're just going to add in an array to memorize the results of the subproblems, and that way we avoid repeating the same work over and over. So if we wrote this in actual pseudocode, what's the order we would fill in this table? So let's say we were looking at the array at some point. We're at I. Before we can compute I, what subproblems do we have to compute? We need to compute splittable of j for all later j's. So, this is some j. We need to compute that j before we compute this I. So if we turn this into a loop, what's the order going to look like? Yes. So it's going to look like this. For I equals n up to 1. We start with the last entry, and then we move up. So basically, you take this for loop for I equals n up to 1, and you're just going to slap this equation inside of it. The equation itself is going to be another for loop. So we plug in for j. Now j, the order of j doesn't really matter. So I'm just going to pick an order. I plus 1. Well, that doesn't make sense. And then we just basically put in this equation. So we'll have s of I equals the previous s of I, or is word ij and s of j plus 1. And at the end you return s of 1. So that's basically the whole algorithm. And this will usually be the case. Once you decide on the structure you're going to use to memorize, and you decided on the order to evaluate all the subproblems, you just plug in your recurrence right in the middle. So once you've figured out the recurrence, this part, you're basically done. This is the hard part. The hard part is coming up with the backtracking algorithm. Adding the space stuff is just mechanical. So any questions on that? That's our final algorithm. Any questions? Yes.
Would that be helpful to add a break if we found some possibilities?
Yeah, so this is called short circuit OR, if anyone's familiar with that. So if you already find one of these is true, you don't have to keep doing this process. The second you find the first true, you can break out of the loop because you know the answer is true. But for us, we're doing algorithms. In the worst case, it's always going to be at the end, and so you can't do that. And for simplicity of the code, we're not going to put like ifs and breaks. But you could definitely do that. In practice, you might want to do that. But remember, we first make it correct, and then we can make it fast. Any other questions? Okay. So this is what's called dynamic programming. It's basically, in one word, recursion without repetition. Repetition is just repeating the same problems over and over. Or I like to make it even simpler and say it's recursion with space. You're using extra space to improve on your runtime. So you increase space to decrease runtime. Okay? That's the pattern. We just take some recursive algorithm. It could be a backtracking algorithm. It could be a divide and conquer algorithm. We don't care what kind of recursion it is. Just take a recursive algorithm. If it's repeating things unnecessarily, memorize those things. And then after you do that, you typically are going to convert the recursive algorithm into like for loops to make it even faster. So the idea here is dynamic programming is not about filling in the tables, it's about smart recursion. So you have some array or some structure that's saving the partial solutions, but that's an afterthought. You worry about that after you've already solved the problem recursively. Don't worry about the arrays or whatever. Worry about solving it recursively first. Okay? Now you're about to see a gigantic wall of text. So, how do you solve dynamic programming problems? This is the key step. So this is the important part. This is what I would call the actual solution. So you want to formulate the problem recursively. This will almost always be the index formulation. So why do we use index formulations? It's so we can use dynamic programming. If you don't have an index formulation, it's very hard to save things in like an array, because arrays use indices. Okay, so you're going to formulate the problem, some recurrence, just like we did for backtracking. So there's two steps. The specification. So again, you're usually solving a more general problem than the original. So for splittable, remember, we only care about splittable of 1. That's the original problem. But we're solving this more general version where you could start in the middle of the array. So because we're solving a different problem from the original, we have to specify in English what we're solving, which is this. Even if your algorithm was perfectly correct, if we don't know what it's solving, we have no way to verify it's correct because we don't know the goals of your algorithm. So that's why it's important to always say in English what problem you're solving. It's not always the original problem. It's usually not, actually. So in particular, this is not how to solve the problem, but what problem you're trying to solve. Okay? The second part is the solution. This is the recurrence. Now you could write it as an actual algorithm in pseudocode, but I generally recommend you write it as a formula, which is this kind of form. It's just, usually simpler. Okay? And this is always going to be recursive, so you're going to have subproblems that are the exact same problem you started with, but with a smaller n, whatever n is, whatever your measure of progress is. Okay, so that's step 1. So this is stuff we've already done. This was all the backtracking stuff. Specifically the index formulation version. So for this part, there's nothing new. We've just spelled it out now. So any questions about this as part of the schematic? This is the most important part. Okay. Here's the second part. This one's the long part, but it's also the easy part. So now once you have your recursive solution, you're going to build up your solutions bottom up. This is where you get the iterative algorithm. So in particular, the first thing you do is identify the subproblems. In the example of splittable, the subproblems would be this. It's the all j greater than I. Those are the subproblems. It's all of these things. In other words, what are the different ways your algorithm can call itself? For Fibonacci, it's always going to be a number between 0 and n. For splittable, it's two numbers, which are both between 0 and n. Or actually, technically, 1 and n plus 1. So this would be ij between 1 and n plus 1 for splittable. Okay. Now we get this giant list of stuff we have to do, but each one's easy. So we have to choose a data structure to store our partial solutions. Normally, it's a multi-dimensional array. So in the examples we saw so far, that's what it would have been, some array. But we'll see examples where you can have a whole graph is storing your solutions. It really depends on the problem. So we choose a data structure to save things in. Then we need to identify dependencies. That was the arrow chart I showed before, where you have I depends on j plus 1. Then you have to find a good evaluation order. That's basically figure out the for loops. Then you analyze the space and time. This is usually the easy part. And then finally, after you've done all that stuff, you write down the final algorithm. So you know which subproblems you want to solve, and you know what order to solve them in. So you're just going to throw those into some loop and do it. That's the final algorithm. Now, creating the final algorithm is kind of mechanical. So for like homeworks and exams, I don't ever expect you to do this. It suffices to say, these are the subproblems, this is the evaluation order, here's the recurrence. And you can always just, plug the recurrence into the for loops, and that's the final solution. So you don't really have to do this step, but I would recommend when you're first doing dynamic programming, just do it so you can actually see the algorithm. Okay, so here's all the steps. I don't expect you to instantly understand them. We're going to go through examples. But are there any questions so far just about what these are asking for? The most important parts are the evaluation order and the dependencies. The data structure doesn't really matter. Identify the subproblems is kind of built into all of it. So those are the two key parts. And just like when you're analyzing recursive algorithms using a recursion tree, you're almost always going to do this by using a picture. Any questions? We're going to go through some examples in a minute. I guess just take it in. Okay. So this is just a quick tangent. What's a greedy algorithm? A greedy algorithm is whatever algorithm you first think of. It's always wrong. That's it. That's the tweet. So really, a greedy algorithm, it usually involves local optima. The key word there is local. So local optima are something that looks really good at the current iteration. So if you had like a for loop and you're computing your maximum payoff over a time horizon, it's saying, well, I'm going to do the best thing right now and kind of hope that that works out. So one really nice example of this, let me move this. So is the explore exploit problem. So you're trying to find, you want to maximize your restaurant experience over your lifetime. And at any given moment, you have to choose a restaurant. So at time t, pick a place to eat. Now, what's one greedy solution? at every time just go to your favorite. That's the greedy solution. So your goal is to maximize your happiness over your lifetime, and to do that, you're going to maximize your happiness at each individual point in time. So if we drew a graph, a local optima would be this, but maybe the global optima is this. So you're getting stuck on a hill. That's what greedy algorithms do. So let's think about it. So if you ate your favorite food every single day, you'd be pretty happy. But what if there's some food that's like way better than your current favorite, but you've just never tried it? So the idea here is sometimes you have to explore new foods to figure out what you really love. You might have found like a 2-star food item you really like right now, but eventually you might find a 5-star item. So really, you could get overall 5 times t, where t is the total number of days you're alive, versus 2 times t. So by doing this algorithm, you're sacrificing in the current moment. You're eating something you don't know for sure will be good, but the payoff is you get more information. You learn the things you like better, so that eventually later down the line, when you start picking your favorite every day, it'll truly be a good option. But if you immediately just pick the best thing every time, your overall payoff could be super small. I think that intuitively makes sense, right? If you just ate the same thing every day, you're never trying new things, you're probably not really eating the best thing you could be eating. Because usually the best things you could eat aren't things you can really eat every day anyway. They're like really fancy places you eat only a couple times. So does this make sense to everyone? So this is why greedy algorithms don't work. Even though they look good in the current moment and they're easy, over a time frame, they're usually not the best thing to do. And in these problems, we're making a sequence of decisions over a time frame, not just a single decision. So greedy algorithms are not what you want to do. Okay? So it's kind of a little, just to give you a gut feeling of what greedy algorithms are and why they're bad. So never use them. Until next week. Never use a greedy algorithm. So in particular, Jeff has this policy, which I'm also going to have, which is if you give us a greedy algorithm and you don't formally prove it correct, you'll get 0 credit, even if it's correct. So just don't do it. Just make a dynamic programming algorithm. They're easier. What just happened? Oh, it got really small. So this is the main takeaway. Whenever you're thinking about using a greedy algorithm, that's your gut telling you to use dynamic programming. Okay? So just convert that voice in your head to the right voice. Cool. So now let's look at some dynamic programming algorithms. So did everyone watch the lecture videos where we discussed longest increasing subsequence? If you have not, no, there's actual. So the last hour of lecture, I made it my office hours, and I made the last hour asynchronous. Yeah. So I posted about this on Piazza. I basically solved one of the homework problems in one of the videos, which I also said on Piazza. Anyway, now you know. So we went through this problem in that video. It's also in Jeff's notes. And now we want to turn it into a dynamic programming algorithm. So before, this was a backtracking algorithm. So I'll just briefly review the problem. But if you want the more detailed one, it's in those videos. So longest increasing subsequence, really simple idea. You have some array of numbers. They're not sorted or anything. They can be whatever. I guess another reminder is make sure you're up to date on Piazza, because I'm posting stuff on there like mad. So you have some array. And you want to come up with a subsequence. So a subsequence means you're just going to select a couple of these in the same order. So like 1, 4, 3, 100. So the order is the same. And you want to pick an increasing subsequence, which means each number increases. So this would be, for example, an increasing sequence, subsequence. If we included 5, it's no longer increasing, so we can't include 5. Yep, 3 would also break it. So if you put 3 here, it's not increasing, so we can't include 3 there. And our goal is just to compute the longest such subsequence. Hence the name. So if you recall, there's 2 main strategies to doing this. One of them is the is this next strategy. So we're going to just grab some position in the problem. We're at an index I. We're assuming we've already decided some things. We already picked a few things. And now our goal is to decide, do we include I or not? Our solution sequence or not? That's the question we're asking. Now, if you recall, you need to remember something about the partial solutions. You can't just pretend they never happened. So the main thing you need to remember is the largest element that you've already chosen. And because you're choosing an increasing sequence, the largest element, and it's always the last one. So you always need to remember AJ, or specifically, you just need to remember J. Where AJ is largest in the tentative sequence solution. Equivalently, J is the last index in the solution sequence. So that's all you need to remember is that J parameter. And then using that J parameter, we need to figure out whether we should or should not include I. And so we try both. So there's 2 options. There's skip and take. So skip says we're just going to recurse on LIS bigger of I plus 1 with the biggest element still being J. Take says we're going to recurse on I plus 1. And now the biggest element is I, because we decided to include it. And then we get plus 1 because we added one thing to our sequence. Okay? And we have to decide between whether we're going to skip or take. And so the idea was, well, if we know that AI is less than AJ, we have no choice. We have to skip. Because it has to be an increasing sequence, right? So if this was J, and it was like 8, and I was 5, well, we definitely can't include 5, because it'd be smaller than the previous thing. But otherwise, assuming that AI is bigger than AJ, then we're going to take the max of both. In other words, we're going to try them both. We just try both possibilities. We don't try to be strategic about which one would make more sense. We just do it. And the recursion fairy will tell us which one is the biggest. Okay? So that's the recursive strategy. So let me just write it in the index formulation now. So LIS bigger of I comma j. This is the length of the longest increasing subsequence for a I through n that must include, or let's just say that is bigger than aj. And then what's the actual recursive definition? We have LIS bigger ij is equal to so let's start with the base case. It's going to be 0 if I is greater than n. That means we've fallen off the array. Obviously, the longest subsequence of nothing is nothing, so its size is 0. Otherwise, if AI is less than aj, we have to skip, and so we just return LIS bigger of I plus 1, j. So the biggest element doesn't change. It's still j, because we didn't include I. We're just going to look at the rest of the array. Then the last case is we have the max of both options. We can either do this again, or we include it, and so we have one more element. And then we have LIS bigger of I plus 1 and I. I is now the biggest element because by definition of this case, AI is greater than aj. So we need all the future elements to now be bigger than I, which is currently the biggest in our subsequence. So that's the solution to the subproblems to this more general problem. But recall the original problem is just to find the biggest subsequence in the whole array. So how do we do that? Well, we're going to return, well, first we're going to set a of 0 to b minus infinity. This is called a sentinel, or a dummy value. Then we return LIS bigger of 0. That's backwards. 1, 0. Okay, so we're getting the longest increasing subsequence of the whole array where everything has to be bigger than a of 0, which is minus infinity. So we do this just to make sure we can always include the first element, because the first element could be really small. So if we don't make a of 0 small enough, our recurrence might always ignore the first element, and we don't want that. So we make it minus infinity to guarantee that it's always bigger than that. Okay, so that's the entire algorithm in the index formulation. Any questions on this? Yes.
For the problem like this where we're trying to find like the optimal solution, I guess, can we just like always assume that the algorithm will go along and pick the most optimal without having to like fully explain it? Like I guess kind of like, I guess it would kind of be like the recursion fair, like I was just trusting it, like.
So the proof of correctness is going to be by induction. And the proof, I don't remember if we did this. Yeah, we did it in class. So the proof for problems like this are, if there exists a solution, it either has the current element I or it doesn't. We recursively check both cases. Whichever one's larger is the one we pick. And so by definition, we have the optimal. But usually for dynamic programming, you don't really have to formally prove it. You just say, it's recursive brute force, we tried them all. I would literally just say the optimal either has that or not, and we try both. And that's like the whole proof. Yes?
What was the point of adding 1 to the list figure function in like, yeah, that case, the max case?
This one?
Yeah.
We added 1 to our sequence, the length. So this is if we include AI. So if we decide to add AI to our sequence, we've added 1 thing to our sequence.
So we're just counting the number of things in the sequence, not the actual elements.
Yeah, but this isn't a like subset sum. It's just the number of things. So if like here, this is a subsequence of size 4. Yep. Okay. So now we need to do all the steps of dynamic programming. I'm going to ignore the proof of correctness because I did that in the video like really rigorously for no reason. So what's the first thing we need to do? We need to identify the subproblems. That's part A. In other words, how many possible inputs could we have to our recursive function? So what values could I take? What values does I take? So we know 1 for sure because we plug in 1 immediately. What's the largest thing I could be? Are you sure? So let's say we plug in I equals n. What's it going to recurse on? Remember, the base case is if I is strictly greater than n. So what's the smallest number strictly greater than n? N plus 1. So I can be any value from 1 to n plus 1. What can j be? That one's j. Yep. So j can be 0 through n. Why? Well, we plug 0 in originally. And then j is always an element of your array. And since the elements only go up to n, j can never be bigger than an. Okay. So immediately I can tell you what the running time is going to be. So how many total subproblems are there? So if we have 2 numbers, each one is O of n, what's the total going to be? It's O of n squared. Because we're putting all possible pairs in there. Any possible ij pair could be in there. Not really, but you know, we're going to worst case it. So in the worst case, there's O of n squared subproblems because that's the number of pairs. Okay? Now B, what's our data structure? What's a convenient data structure that can hold pairs of numbers? Yep, a matrix, we'll call it a 2D array. So a matrix slash 2D array. So I'll just call it S. I don't like that. I'll call it L. So LJ. this entry is going to be, or we can also let's just call it L, comma J in good Python notation. This will be the subproblem ij. So it's a 2D array, so we're using n squared space as well. I don't know why I switched from green. That was weird. Okay. Any questions about the data structure and subproblems? Cool. So what was C? This is problem dependencies. This is where it's going to get crazy. So this is the main hard part of dynamic programming. So this is exactly what I want you guys to do on the homework. You're going to draw your data structure. Okay? So, whoa, that's a long boy. Okay. So we have I goes from 1 to n plus 1. Then we have j, which goes from 1, no it doesn't, from 0 to n. So this is just a picture of our 2D array / data structure that we're going to use to store subproblems. Now let's look at the ijth subproblem. So this is I comma j. Now what does I comma j depend on? We're just going to draw it. So let's look at the recurrence. So I comma j depends on I plus 1j and I plus 1I. So the subproblem dependencies are ij depends on I plus 1j and I plus 1I. So visually, if I is our row, we have an I plus 1. This is I plus 1j. Whoa. Okay, so this is I plus 1j. Now, where's I plus 1I? Well, I could be anywhere, really. Doesn't matter, so I'll just draw it over here. Okay, so those are our two subproblems we depend on. And now you're just going to draw arrows. And what these arrows mean are that our subproblem ij needs these two to be computed first before we can compute ij. Or in other words, ij calls recursively these two subproblems. Okay? So these are our dependencies. If I had to summarize this in one word, I would say we need to compute the I plus 1th row first. It doesn't really matter the order in which we process each thing in the row. All that matters is that we have this row already completed before we go on to the next row above. Okay? So part D, which is the evaluation order, that's kind of built into this picture. So the evaluation order is going to be this. So this double arrow, this means we're going to process all of our data row by row, starting from the bottom and going up. So that's what that means. Just saying we're going to do, this. So that's our evaluation order. One more page. Okay. Any questions on the picture so far? Yes.
Are you going to want us to upload that to our homework, like a picture, like every time?
Yes. Yeah. So that's what I used to do when I was taking the class. You can do it in LaTeX if you want. There's a way to do it. It's not that hard. But I think it's easier just to like take a picture and include it in your document. And on exams, you always, of course, want to draw this. So just like with recursion trees, every time you have a recursive algorithm, you're drawing a recursion tree, usually. You're almost always going to be drawing this dependency graph when you're doing dynamic programming analysis. Okay? Now the next one is runtime, space complexity. So what's the runtime? So we know we have O of n squared subproblems. Now assuming we've already computed the recursive stuff, how long does it take to solve the ij subproblem? Ignoring recursion, how much work do we do? So let me rephrase. What work do we do, ignoring the recursion? Yes?
You take the maximum of two values and maybe do some addition.
Yep, so all we're doing is we have like an if statement, we have a max of two things, and we have a plus. So that's constant work to me. I don't know about y'all, but I think that's pretty easy. So per subproblem, ignoring recursive stuff, or assuming they're already computed, then we're doing O of 1 work per subproblem. So if there's O of n squared subproblems, each one's constant work, well, they're just going to multiply. So the total runtime is just going to be O of 1 times O of n squared, which is O of n squared. The space complexity is O of n squared. That's just the size of your array. Okay? Any questions on that? And the last step is to put it all together. So I'll just show you the algorithm for LIS. So here's the recurrence we already have. There's the chart. I just drew it in reverse. So here's the final algorithm. So the main differences here are you're initializing your base cases into the storage array. That's whatever. The main thing here is our evaluation order becomes 2 for loops. And the rest of it is just the recurrence. We just slapped everything in the recurrence right into the for loops. And then we returned the final value. So the final result is literally you just picking the order of the loops and then just slapping your recurrence in the middle. So it's almost immediate. It's very mechanical. But if you're curious, that's what it looks like. Okay. So that's it. That's the full process. So just to be precise, there's actually a second arrow. So our second arrow here, which is the inner for loop, is going to be, it doesn't matter, we can just pick one, so I'm just going to pick this. So that's saying I is in the outer for loop, that's the double arrow, from n plus 1 up to 0, or up to 1. And j is going to start from 0 and go up to n in an inner for loop. So that's what that means. The order of I is critical to the correctness of the algorithm. The order of j is irrelevant. So you could do whatever order you want over j. You could do some weird start in the middle and like go back and forth. It doesn't matter. Just pick something. Preferably simple, like 0 to n, not some weird skipping thing. Okay? So basically, the main steps here are create this recursive problem, define a recursive problem, solve the recursive problem. Usually you have giant curly braces to do that. And then draw this picture. This is the important part. This picture is encapsulating kind of everything. You have your data structure drawn, you have the subproblems there, and you have the dependencies, and you have the eval order. So I've kind of baked in like A through D all into one picture. But when you're just starting out, I do recommend you go through each step individually just to get it clear what everything is. But this is the key step. This is the dynamic programming part. Any questions? Yes.
Why is it better to pre-compute the whole grid rather than just computing the row that you need when you need it?
It's not better. So this is another thing. You start easy and then you can improve it. So really, you don't have to remember all n squared subproblems. You just need to really remember this row. So, after you've done the whole process, maybe you notice, hey, we don't need all this space, and then you can update your algorithm to just use the previous row, and then you get O of n space. But always start here. Start easy first, and then think about how to improve the performance. Because usually it's an easy tweak, right? So after you have the original algorithm, just a small little tweak in the beginning, and you get the improved performance. Instead of having to worry about in advance of creating a much more complicated algorithm. So I'll just mention it can be reduced to O of n. Okay. So now we're going to do the same thing again using the what's next recurrence for LIS. So in the previous recurrence, the main idea was we decide, will AI be next or not? Should we include it or not? So before we were looking at AI, include it or not. Now let's just assume we're including it, okay? So just assume we include it. So we need to decide what comes next in the subsequence. Okay? So I'm just going to tell you what the recurrence is, because the focus here is the dynamic programming. So LIS next of I is going to be 1 plus the max overall j greater than I of LIS next of j plus 1 if AJ is actually greater than AI. That's the entire recurrence. We didn't even need big curly braces. It's one line. So the cool thing about this recurrence is the base case is built in. So the max of the empty set is going to be 0. And so LIS next of n will be 1, which is correct, because it has only one element. So the base case is built in. It's really nice. Now again, we kind of need to do a sentinel thing. So again, we're going to say A0 is minus infinity and return LIS next of 0 minus 1. So this is going to forcibly include A0, but A0 is obviously not actually in the array. So we're going to subtract 1 to kill the 1 that we added incorrectly. Alternatively, you can just return the max over all I of LIS next. That also works, whichever one you prefer. Okay? So that's the full algorithm. That's the specification. So now let's do the DP stuff. So A is identifying subproblems. So what are our subproblems here? So we have a subproblem for each I, right? So what can I be? Yes. So I can be 0 up to n. It will never be n plus 1 just because if we plug in n here, the max will be empty because there's no j greater than I. So in this recurrence, I won't actually go to n plus 1. It'll stop at n. So we have O of n subproblems. So already this is looking kind of nice, right? We have significantly fewer subproblems than before. So you might be thinking that this is a way faster algorithm. Maybe it is. We'll see. Okay, what's our data structure? How can we store n plus 1 subproblems? What's a simple data structure that can store n things in a row? I hear whispers. Somebody say it. An array, yeah, so we'll have an array. What should we call this one? I'll call it M for memorize. So we have an array that's indexed from 0 up to n, so it can store all of our subproblems. Cool. C. So we're at the problem dependencies. This is where we're going to draw the picture. The picture is a little easier this time. So we have subproblem I. What does subproblem I depend on? If we look at the algorithm, it depends on j plus 1 for every possible j greater than I. That should be at least I, actually. Okay? So basically, it depends on all previous things. So I depends on every j that's over here. Just all of them. Depends on all of them. Okay, so we see the subproblem dependencies. I depends on all the future subproblems. So what's a good eval order that guarantees those are computed before I is computed? Okay, I saw hand movements, that's good enough. So we're going to compute I from the end to the beginning. So this is our eval order. Okay. So again, like I originally mentioned for Fibonacci numbers, the idea is we're doing bottom up. We start at the leaves, and then we go back to the root. And even for arrays, it's the same thing. We're starting at the leaves, which is now n, and slowly pushing our answers up the tree to the top, where the root is now 0. So you could think of this as like a path tree, which is a super skinny tree, and we're still doing the same kind of idea. Any questions on this picture? You're going to see this picture 1,000 times. Okay. Eval orders built into that part, so now we're at E. What's the running time and space complexity? So the space complexity is, again, it's just the size of the table or the size of the array. Now what's the time? So we know there's O of n subproblems. But how much work do we do per subproblem in the worst case? Yes, so the answer is O of n. Why? Because that max right there is basically a for loop over all possible j. So when I is pretty small, when I is close to 1, you're looking at almost every single thing in the array. So for each subproblem, you're doing n minus I work. Which is O of n. Okay. So overall, you're doing O of n subproblems, each taking O of n time, so it's O of n squared. So although it may have looked like we were getting a much better algorithm, asymptotically they're actually the same. We didn't really get significant savings from doing it this way. But we did get space savings if you just look at the originals. You can also improve the space of the previous one too. So they're basically the same algorithm, even though they function completely differently. So then lastly, step F, that's where we just plug it in. So if we look at this, that's it. So again, we have our for loop from n at the bottom all the way up to 0. And then we're just doing exactly the stuff in the curly braces. We take 1 plus whichever is the best one. We're just taking a max over all of them. Okay? So that's the whole thing. Any questions on that? Any questions? So the next one's going to be very different. So if there's questions, let me know. Yes?
Would you mind to elaborate on the base case that a to 0 and then equal to negative infinities? Also like
So that's there because we're doing a max over, it's the same reason we had this base case before. So a0 is minus infinity so that we can always take the first item. If you made that anything else but minus infinity, a1 might be less than it. And if a1 is less than a0, then it'll never be chosen in that max because it doesn't satisfy that condition.
okay, and what about like the part when they're in the return statement, the war max I,
So that's just an alternative. So you can either use the sentinel a0 or you can just return this. Basically, the max one is saying, what's the best first thing? What's the best first element for your sequence? And you just try all possible first elements. Yes?
I don't understand the notation that you're using for max. Like, what does that mean?
This is the max over all indices j that are larger than I. So it's like a for loop for j from I up to n, and then you do max stuff. You'll compare it. Other questions? And of course, I elaborate more on where this comes from in the video. We're more focused on how to make it a DP algorithm. No, they're released after, because it's the last hour of lecture. So it depends on what we did in lecture. Does the picture make sense? Cool. So now we're going to do something with trees, because I love trees. So this is the maximum independent set problem. This problem's pretty simple. It's how do you sit people at a wedding when people hate each other, and you need to take that into account. So you have some graph, and an independent set just says no neighbor is connected in your set. So if our set is the green, if that's in our set, we cannot choose any of these. None of those are allowed. You can think of this as like a hatred graph. Two things are connected if they hate each other. And so you don't want to include any pairs, anything connected. So for example, that's an independent set. Nothing in the set has an edge between anything else in the set. So there's nothing like this. And our goal, as you could imagine, is to compute the max independent set in a tree. So you want to maximize the number of guests you can invite to your wedding. So here's a picture. So if you include the root of the tree, you cannot include any of its children because there's a direct edge to it. But if you don't include the root, well then you can possibly include the children if you want to. So is the problem statement clear? Just a picture, but I hope that makes it clear. Okay? So this is kind of tempting us with how we should solve this. So we want to break this into some decision procedure. And the decisions we're going to make are, should we include the root or not? So let's say max independent set of V is the size of a max independent set in the subtree rooted at V that must include V. And this is really common for tree problems. You're usually going to define this thing so that it forcibly does something to the root every time. That's pretty common. And this is what you did for problem 3 from last homework too. Okay, so that's what we want to define. Now I think it's kind of obvious, so we have to include V. We're kind of restricted if we do this. So if we have to include V, then we always have to skip the neighbors, right? So for this problem, we actually don't want to do that. That's all we want to do. Okay? So then we have the option. We can decide, do we want to include the root or not? So the key idea is include the root, which is V, or not. Okay. So let's actually solve the problem. Actually, we don't even need curly braces. So we have two options. We can skip V or include it. So let's take a max. Let's say we include V. Actually, let's not include V. So we don't include V, then we are allowed to include all of the children if we want to. So we're really just solving the same problem now, but on each child subtree. We can take those roots if we want, or we cannot. We don't care. We're going to let the recursion theory deal with those details. So this is just going to be the sum of all children. So this arrow notation means that W is a child of V. So something like this. Of the maximum independent set of W. So that's if we skip V. Now if we include V, we instantly get a 1 plus because we added one more node to our set. But now we have to skip our children. So now we're going to sum over all children and sum over all their children, so your grandchildren, of the maximum independent set of U. Okay, so the idea here is if we don't take V, well then we can, if we want to, take the children. We'll let the recursion fairy decide if we should do that. Otherwise, if we do decide to take V, we get a 1 plus, but now we have to skip all of W. We skip the children W. So we skip the W's and go straight to the grandchildren and repeat the process. The base case is built in because if V is a leaf, if it has no children, then this is going to be 1 plus 0 because those sums will be empty sums. And so we correctly get out the maximum independent set of a leaf is just 1. Okay? So what's our final output? Remember, we're solving a more general problem. So what's the original problem we wanted to solve? And how can we use this to solve it? What are we returning at the end? Of what's the input? The root, yeah. So we're returning maximum independent set of R, which is the root of the entire tree. So this just says, give me the max independent set of the whole tree. Okay? So any questions about the algorithm? If we look at it pictorially, that's what it's doing. It either takes V or it skips V and then chooses the best of both. And it recursively computes either the children or grandchildren depending on whether we're allowed to include the children or not. Any questions? Okay, so let's do the DP stuff now. What are our subproblems? Yes.
Maximum independence of W, maximum independence of U.
Yeah, so for the overall process, we have one subproblem per node. So we have one subproblem per node, which is just MIS of V. So in total, we have O of N. N is the number of nodes. Okay?
How does it know before N is the maximum?
This is just the number of subproblems for the whole process. So what possible things can you plug into MIS? That's what the subproblems are. So you could plug in the root, you could plug in a leaf, you could plug in any node. Similar to like LIS, you could plug in any entry, I through 0 to N. So that's what the subproblems are. You're thinking of dependencies, which is similar.
How is the base case built in? Like base case will be for leaves, right?
Yeah, so if you plug in a leaf, it has no children, so the sums are 0. So you get the max of 0 and 1 plus 0, which is 1.
But we still have to define it, like if it's a leaf, then output 0.
If you made like an actual pseudocode, yeah. If you do it mathematically, that's built in, which is why I like the math one better. So what data structure should we use? I mean, should we use an array? Yes. Yeah, so we're going to use the tree itself. So the most natural way to store things about the tree is to use the tree. Like, you already have this space in your memory dedicated to the tree, so why waste more memory by making some other complicated data structure? So in particular, for each node, you're going to add like an attribute, MIS. And this is going to be MIS of V. You could use an array or some kind of like hash table that maps V to some unique element, but that's too complicated. We're just going to do the simplest thing, which is use the tree itself. Okay? So now let's look at the dependencies. So if we draw out our tree, so let's say we're here, this is V. V depends on its children and its grandchildren. So we have arrows here, and we have arrows here, just a bunch of arrows. It does not depend on its great-great-grandchildren, though, so that node would not have an arrow. Okay, so those are the dependencies. So each child and grandchild. Now, what's a good evaluation order that guarantees we hit the children and grandchildren before hitting V? Got to pull this from CS300. A depth-first search, I think that works. Yeah, so a depth-first search works, but there's a more general class that does the same thing. It's called a post-order traversal. So post-order traversal, if you remember like graph searches, it says you visit you recurse on the left and right, and then you visit your node. So you visit the parent node last. And that's just one specific version of a DFS. So this is just a like more general version of DFS. But just say post-order traversal. We can compute those. And that definitely ensures that our subproblems are evaluated before V is. So if you want to draw it pictorially, just have this giant arrow here. Okay. So that's also D, the eval order. So this is F. This is the actual algorithm. It's going to implement exactly what we just said. So we have the skip, we have the keep, so that means we take V or we don't. Then we loop over all the grandchildren if we do keep it. We just loop over the children if we skip it, and we take the max of both. So this is take V, skip V. Now you'll notice something. So you'll recall, like in most DP algorithms, in the end, you really have a loop. You're not doing any recursion anymore, explicitly. But here, we're actually explicitly using recursion. Why do we do that? Well, because that's how you implement a post-order traversal. So that's why we actually have recursion built in here, because that's doing the post-order traversal. Now, what's the running time? So the space is O of n, because we added like one thing per node. Now, what's the running time? Now, you could try to come up with like a recurrence based on, V has, it calls the algorithm on all the children, and you could try to figure out some recurrence, but don't do that because it gets really complicated. The way you want to think of it is assuming we've done the recursion, how much work do we do per node? And how much does that node contribute to the top nodes? So in particular, every node contributes 1 to its parent. So instead of looking at V and seeing what's going on down there, we look at W, the child, and say, okay, for W to contribute to V's count, we just do one addition. That's because of the one addition right here. So if each node contributes constant to its parent, then we have O of 1 per parent, and that's O of n for the whole tree, because there's n total parents in the tree. Another way to think about it is how much work do you do per node? That's the way you want to think about it. It's not technically the same, but that's just how you should think about it. So per node, ignoring the fact that we have like 1 million children, we're doing O of 1 work. This is a way to just get around the fact that you could have many children and this tree is skewed. Okay. So any questions on that? Yes.
Oh, would you want to elaborate on the conditions x.mis?
Yeah, so we just added a new attribute to each node. So if you had like a node class, you can just add an attribute to it.
Is that just saying that's the minimum whatever set for that node?
This is exactly the solution to this subproblem. So you're going to store that solution into an attribute at the node. So it's the maximum independent set that's on the tree rooted at node V. So essentially, you're computing all of these, and then you save it to a variable inside the node itself. Yes?
Why is max of curly braces?
Because it's just a max of. Well, this is just a mathematical notation. You could put parentheses if you prefer. So math people do this because it's a max over a set. We think of it as like a set instead of a function, but they're the same thing. Yes?
So for like the skip V portion, it's skip V plus tree MISW.
Mm-hmm.
Keep V portion, it's keep V plus x dot MIS. So x dot MIS is just tree MIS x just stored for 2x.
This is the stored version, yeah.
So
So when you call this recursively, you will populate the grandchildren's entries.
well, that's why it's tree MIS on the top and not it's x and x on the bottom.
Yeah. So once you go down there, you've already filled up those nodes, so you don't have to call it again. Other questions? Feel free to leave too, by the way, so lecture's technically over. I'll be releasing the next video in a couple of hours to give more DP examples. If you haven't watched the previous videos, please do.
The previous videos